So moving on to the next section, what is the next section? Advanced functions and closures. Chapter 19, section 4. All right, let's get it. Finally, we'll explore some advanced features related to functions and closures, which include function pointers and returning closures. That sounds useful. Function pointers. We've talked about how to pass closures to functions. You can also pass regular functions to functions. This technique is useful when you want to pass a function you've already defined rather than defining a new closure. Doing this with function pointers will allow you to use functions as arguments to other functions. Functions coerce to the type fn, notice the lowercase f, not to be confused with the capital Fn, closure trait. The fn type is called a function pointer. The syntax for specifying that a parameter is a function pointer is similar to that of a closure, as shown in listing 19-27. Alright, so we're going to learn how to pass functions into functions. That sounds good. So here we have add1, takes I32, returns I32, just adds 1 to whatever x is, cool. And we're doing it twice. So you take the function, which is going to be the add1 that has the signature, I32, and an argument, which that's going to be the argument that's going to be passed into this function, which you can see here. And this is doing it twice, so it's just calling the same function twice. And then we have main, and we're doing it to 5. So yeah, this is definitely something we can test out. We don't need you. Everything look good. And yeah, the answer is 12. So 5, add 1 to it twice, which is 6. And then you get the other 6, and then you add those two together, which gives you 12. All right. This code prints the answer is 12. We specify that the parameter f in do twice is an fn that takes one parameter of type I32 and returns an I32. We can then call f in the body of do twice. In main, we can pass the function name add1 as the first argument to do twice. Unlike closures, fn is a type rather than a trait, so we specify fn as the parameter type directly rather than declaring a generic type parameter with one of the capital Fn traits as a trait bound. Function pointers implement all three of the closure traits, capital Fn, capital Fn mute, and capital Fn once. So you can always pass a function pointer as an argument for a function that accepts a closure. It's best to write functions using a generic type and one of the closure traits so your function can accept either functions or closures. I see. So here I believe what they're saying is, given that functions always support the 3 different trait bounds for closures, if you write your functions in such a way that they accept a generic type, then anywhere you can pass a closure, you can pass a function, and then you could just use that syntax for the closures everywhere, given that you wrote your functions that way as well. An example of where you would want to only accept lowercase fn and not closures is when interfacing with external code that doesn't have closures. C functions can accept functions as arguments, but C doesn't have closures. As an example of where you can use either a closure defined inline or a named function, let's look at the use of map. To use the map function to turn a vector of numbers into a vector of strings, we could use a closure like this. So we have a vector of numbers, 1, 2, 3, and we want to make it into a vector of string, which we put here as the type. We have the list of numbers, and then we're calling iterator, which is not going to act until we collect on it. We have map, which we're doing I, here's the closure within the map. Everything here to string, and then that gets returned, and collect, let's do the final, to run the iterator. Consume it, that's the word. Or we could name a function as the argument to map instead of the closure, like this. So we have same thing here, vector of numbers. Same thing here. We have the numbers, we have the type that we want, vector of strings. We have an iterator, but in the map, instead of writing a closure like we did here, it looks like we just have the toString, I guess, namespace, and calling, or the toString struct, whichever, and calling the toString method, and that seemingly is going to be called on all of them. So this is the function that takes in the argument, seemingly, and then collect. Note that we must use the fully qualified syntax that we talked about earlier in the advanced traits section, because there are multiple functions available named toString. Here, we're using the toString function defined to the toString trait, which the standard library has implemented for any type that implements display. I see. So this is the trait, and we're using the explicit syntax to make sure that we're calling the toString from the capital T toString trait. And that's always going to be there as long as something implements display, which numbers and strings both implement display. Anything that can be printed implements display. We have another useful pattern that exploits an implementation detail of tuple structs and tuple struct enum variants. These type use parentheses, you can see like open and close, nothing in it, as initializer syntax, which looks like a function call. The initializers are actually implemented as function returning an instance that constructed from their arguments. We can use these initializer functions as function pointers that implement the closure traits, which means we can specify the initializer function as arguments for methods that take closures like so. I didn't understand a word of that. Let's see what they do here. Enum status, value, stop, okay. List of statuses. We have a vec of statuses, understood. We're doing a range from there to there, and we're mapping status to value, explicit syntax, seemingly, and then we're collecting. Here we create status value instead of using each U32 value in the range that map is called on by using the initializer function of status value. Some people prefer this style and some people prefer to use closures. They compile to the same code. So whichever style is clear to you. This is not clear to me at all. I mean, I guess this is an explicit method call, and I'm guessing you're passing in the number in it always. But no, that's not clear to me. I'm a closer person. I'm gonna stick with closures. Returning closures. Closures are represented by traits, which means you can't return closures directly. In most cases, where you might want to return a trait, you can instead use the concrete type that implements the trait as the return value of the function. But you can't do that with closures because they don't have a concrete type that is returnable. You're not allowed to use the function pointer fn as a return type, for example. Let's continue reading and see exactly what they mean. The following code tries to return a closure directly, but it won't compile. Okay, so they got that point across. You can't return closures, and you're not allowed to return a pointer to a function. You get the following error. The compiler gives you the following error. Does not have constant size known at compile time, which makes sense. Closure. The error referenced the size trait again. Rust doesn't know how much space it will need to store the closure. We saw a solution to this problem earlier. We can use a trait object. I see. You can put the closure within a box, and then you have a pointer to the closure, and then returning the pointer, which is sized. Yes, you can do that with anything. Okay, yeah, that makes sense. And then I guess this way you can return closures if you wanted to. This code will compile just fine. For more about trait objects, refer to the section using trait objects that allow for values of different types in Chapter 17. Now, let's look at macros. Alright, that was a short video. We hit the end of it. If you like it, hit like. If you want to subscribe, subscribe. Outside of that, until next time. Peace.